we draw it as if it were a one-dimensional molecule. Now in the Chem 101 app, they actually show this molecules like this more in three-dimensional space, which is good because this flat representation is false. And we're going to tackle today why flat Lewis structures, while useful, are not truly representative of how most molecules orient themselves in space. So we're going to be looking at something called bond angles. Between any two given atoms in your molecule, there are bond angles, and we want to know what they are, depending on what kind of molecule we're dealing with. This will require us to evaluate both bonding electron pairs and non-bonding electron pairs. So this is intimately related to Lewis structures, but it takes it to, you know, it's like Emeril would say, we're going to kick it up a notch because we don't have the whole story yet. And this is based in this kind of strange term, which is VSEPR is usually how it's pronounced, or VSEPR, or valence shell electron pair repulsion. This is a theory of bonding, and it enables us to actually understand something real, let's say, about molecular geometry. But I want to remind you first, quickly, what we know how to do so far. We know how to draw electron configurations, you know, things like 1s2, 2s2, 2p6, you know, I could go on all day here. We know also how to take something like this and represent it in an orbital diagram, and it requires us to build up electron by electron. And we know it's always going to be the outermost electrons with the highest n number that are going to give us our valence electrons, right? When we know what our valence electrons are, we're able to draw Lewis structures that include covalent bonds that are based on electron sharing. Now what we're going to bring that together with on some level in order to understand this idea of geometry is remember that things like NS, P, D, and F orbitals have orientations in space, right? We talked about that extensively. P orbitals have 3 different orientations, for example. So if we're going to get at 3-dimensional space, we need to understand something about orientation, because the electrons live inside these orbitals, right? And they live inside orbitals that are oriented to one another differently. So this is just example for nitrogen, how you could draw an electron configuration and an orbital diagram. This is just typical example of a Lewis structure, been there, done that. And this is a recapitulation of all these molecular orbitals. And, you know, as always, I always go back to the p orbital because I think it's both not overly complex, but also very illustrative. Each orientation of a p orbital, I remind you, can hold up to 2 electrons. One orientation of one orbital can hold up to 2 electrons for a total of 6 electrons. And each of these are at 90 degrees to one another. This one's on the x-axis, this one's on the z-axis, and this one's on the y-axis. So they're at right angles to one another. Okay, and we get, you know, it gets obviously more complicated down here, but we still understand that these are all at different orientations. So getting back to this idea of VSEPR, We want to be able to predict the geometry of the molecule. And this is the key. From the electrostatic repulsions between electrons, both bonding and non-bonding pairs. The geometry that the molecule assumes, the different bonds and the lone pairs themselves will move into 3D space in order to get as far apart, as far away from one another as possible. Why do you think electrons want these bonding and lone pair electrons? Why do you think they want to be far away from each other?
Maybe it creates the most stability.
Yeah, that's true. What literally drives the fact that they want to be away from each other? What drives them apart? It says it right here in this boxed statement. What's the key statement that tells you that electron pairs don't want to be close to one another?
Repulsions.
Repulsion, right? Negative, negative. They don't want to be right next to each other. So they're going to orient each other as far apart as possible. But this is going to depend on how many bonds there are, how many lone pairs there are. That's going to directly impact how they can orient themselves as far as possible away from one another. So now we have to go through case by case by case, because we know there's a lot of variation within Lewis structures. We can have 3 bonds, 1 lone pair. We can have 2 bonds, 2 lone pairs. We can have just all 4 bonds. We can have a lot of stuff, right? So in order to attack this in an ordered fashion, we're just going to have to go through this in this table-like fashion. And we're going to consider it by something called class. And for each class, we're going to consider how many atoms are bonded to the central atom, and also the number of lone pairs on the central atom. So again, we're going to be considering bonded atoms and lone pair atoms on the central atom. Then we're going to compare what we call the arrangement of the electron pairs and how that relates to something called the molecular geometry. So what's the first class we're going to deal with? We're going to call this AB2, and this is like code, basically. What does AB2 mean? It means we have a central molecule bonded to 2 atoms of B. So by definition, we're going to have 2 bonded atoms, 0 lone pairs. It's going to be a linear molecule, and it's also going to have a molecular geometry that is linear. I'm going to be explaining the difference between these 2 things when we get to a more representative example. But a classic example of this would be BeCl2. Beryllium is our A. The chlorines are our B2. There are, therefore, 2 atoms bonded to the central atom. We already saw beryllium dichloride doesn't have any lone pairs, right? So 0 lone pairs. These bonds can get as far apart from one another as possible by assuming a linear conformation. If it were to look like this, for example, that wouldn't make any sense, right? Because these 2 bonds would be much closer to each other. So this assumes a linear conformation, BeCl2. And there you have it in illustration form. Okay, next. Next class is AB3. So remember BF3, also an incomplete octet. So if we think about BF3, how many atoms do we have? Well, we're told right here we have 3 atoms bonded to the central atom. By definition, when we're considering a molecule like BF3, there's going to be 0 lone pairs bonded to the central atom. What could the arrangement be so that these molecules are as far apart from each other as possible? What would you do if you had a B and 3 Fs? What bond angles do you think would enable these fluorines that are bonded to the central atom be as far away from each other as possible? 120 degrees, absolutely. And we'll see that in a minute. So this has a name. We're going to call it trigonal planar. And this is how it looks. Now notice that they've put little electrons around the bottom here. These really just represent the bonding electrons from this bond. That's not a lone pair. Don't let them confuse you into thinking that's a lone pair. Those are just the atoms that are bonding the fluorine, really, to the central molecule. But you omit any sign of electrons when you do the molecular geometry. And again, we're not at a point. Notice for every example that we've given so far, the arrangement of the electron pairs, or something called the electron pair geometry, is another way this is identified, and the molecular geometry are the same. This is not always true. So be prepared for incidences where this is not true, that they're actually, the electron pair geometry and the molecular geometry are in fact different. So this is still, notice, I made a big deal about, oh, we're going to move into 3-dimensional space, and we haven't done that yet. For beryllium chloride and for boron trifluoride, we have 180-degree bond angles in the first case, 120-degree bond angles now, but still a flat planar molecule. Now things with AB4. What does that sound like? That sounds something like methane, right? So 4 atoms bonded to the central atom, 0 lone pairs in methane around the carbon. Now we get to something different looking. We get to something called tetrahedral. Because if you think about the challenge of arranging 4 hydrogens around your molecule and maximizing the distances between these 4 molecules, if we just drew it like this, like Lewis structure, how far apart would each of these bonds be from each other?
90 degrees.
90 degrees. That's not, let's just say that methane can do better. Methane can do better than that. If it orients itself in space like this, the bond angles can be 109.5 degrees, which is obviously larger bond angle than 90. So we have something, sticking out here. We have it's a tetrahedron. We have something kind of pushed back here, coming out of the plane a little bit, and this one is in the plane here. So this is a tetrahedron. And you're going to be seeing a lot of tetrahedral molecules. Once again, the geometry, molecular geometry is the same. So here it is, your typical tetrahedral molecule. It could also be, for example, CCl4. Same idea as CH4 in terms of assuming a tetrahedral geometry. AB5, what molecule did we just see earlier in lecture that has the central molecule with 5 things bonded around it? PF5, thank you. So once again, we keep building up here. Things are getting a little more complicated each time. This, you're going to see these structures get more and more complex. So this is PF5, let's say. Our P is in the middle here. That isn't well drawn. This is our P, and these are all our Fs, orienting themselves around the molecule. So there's a couple different bond angles going on here. Notice that we have both 90-degree bond angles between 2 of the fluorines and the phosphorus. We have a 90-degree bond angle, or I should say the 2 fluorine bonds. So between this fluorine bond and this fluorine bond, we have a 90-degree bond angle, okay? And there's 2 of those. Between, if you look carefully here, you'll see we also have bond angles of 120 degrees. So when we put all this together, we get a shape that is called trigonal bipyramidal. Why is that? Well, it's 2 pyramids face to face, right? With this triangle base here. So that's why it's called trigonal bipyramidal. Arrangement of electron pairs and molecular geometry is the same. So here you see it again, a little more clearly for those bond angles, right? The 90 and the 120. And that's what's going to minimize repulsion. Again, remember, this is all about minimizing repulsion. AB6. Okay, this is something we also just saw a short time ago, something like SF6. 6 atoms bonded to the central atom. Octahedral geometry. Notice all bond angles are 90 degrees. It is an octahedron. It has this, would have 8 faces basically, right? And it has this rectangle or square in the middle. Octahedral for SF6. Okay. So we've gone through all of that. Phew. Kind of a lot to take in, but not impossible. These are quite easy, right? Tetrahedral, you're going to see all the time. You're going to get used to that. These are a little more, going to have to memorize those. Here is a summary of all of this, which is pretty handy. And some representative examples for each category. So these tables are good for when you're studying, right? It's sort of one-stop shopping. Why do they bother with the lone pair? Are you talking about, Christian, are you talking about putting these in? Is that what you mean? If that's what you're talking about, we need to, I keep promising I'm going to explain this to you. We're going to distinguish between electron pair geometry, EP geometry, and molecular geometry, because they can be different. But we haven't gotten there yet. We're going to get there right now, I promise you. And then I think it'll make more sense to you why we make these different kinds of notations on both sides here. Okay, before we move on quite on to that though, I wanna, well, this does introduce, in fact, a structure where you have, so this is methane, and we just have 4 covalent bonds. Here for NH3, we have 3 covalent bonds, 1 lone pair. Oops, 4 covalent bonds. And then over here we have 2 bonds and 2 lone pair. Now there's a couple things that are interesting here. Notice that when we think about the geometry of each of these molecules, they are all, in terms of electron pair geometry, they are all what shape? You tell me. What are each of these in terms of their electron pair geometry? Tetrahedral. So you might find this a little more confusing for NH3. But remember that when we're talking about repulsion between bonding pairs of electrons, well, let me do this again. These 2 bonds have repulsion to one another, as do these 2 bonds. There is also repulsion between this bond and the lone pair on both sides, right? So when we're considering geometry of the molecule, and we're including both the covalent bonds and the lone pairs, that dictates the overall electron pair geometry, tetrahedral. Same thing here. There is repulsion between these 2 non-bonding pairs, between these 2 lone pairs. There's repulsion here. There's repulsion here. Repulsion everywhere. Okay. So, but there's one thing to keep in mind. Notice that in the tetrahedral bond, we said all bond angles 109.5. But here in NH3, the bond angle between these bonded hydrogens has gotten a little bit compressed. And it's gotten even more compressed in this molecule, which is water. Why? Well, the reason is the lone pair exerts even more repulsion relative to the bonding pairs than the bonding pairs do to each other. And it becomes more extreme in this case because we have 2 lone pairs compressing the bond angles. So keep in mind that if you have, if you're considering a tetrahedral geometry for something like ammonia or H2O, these bond angles get compressed. And the kind of rule is lone pair versus lone pair repulsion is the greatest. So these 2 are particularly strong. Lone pair versus bonding pair repulsion is the next strongest. And then we have bonding pair versus bonding pair repulsion third. Now, is a good place for me to illustrate to you the difference, and I'm going to go into it again, but this is a good place to illustrate to you the difference between what I keep referring to EP geometry versus molecular geometry. So this molecule, NH3, in terms of its electron pair geometry, is decidedly tetrahedral. Because we have this lone pair here, as well as all of our bonding pairs. Anyway, I'm trying to do a tetrahedron, not having a lot of success here. What if we were just to consider the geometry of our molecule to be this? That looks like a different shape, right, than the tetrahedron itself. Also for water, if we were just considering the molecular geometry, and we just looked at this and we didn't think about the lone pairs, which do impact the overall geometry, but let's say we just want to consider what the geometry is of our bonding pairs, well, water becomes something called bent in terms of its molecular geometry, because this right here, it looks bent, right? It looks like you took a stick and you bent it. However, while the molecular geometry of water may be bent, the electron pair geometry is tetrahedral. Does that make sense to people? Adrian, it's not just 4 atoms bonded. Well, that is one way of describing tetrahedral. But the point I'm trying to make here, if you look at nitrogen, if you have 2 lone pairs around your central atoms and 2 bonded atoms, it is tetrahedral in terms of its electron pair geometry, because these lone pairs are repulsed by one another, just like the bonding electrons are. So look up here and notice why nitrogen is a tetrahedral molecule, because this lone pair here impacts the geometry. So everything can be as far away from one another as possible. It's also true for the tetrahedral molecule, where 4 things are bonded. And water is also tetrahedral, electron pair geometry, but bent in terms of its molecular geometry. This here, if we wanted to identify the molecular geometry, is trigonal pyramidal. So let's move on in terms of the classifications, and hopefully this will become even a little more clear. So here's a good example of a distinction between the arrangement of all the electron pairs. Keep in mind, this means bonding plus non-bonding, where here we're basically considering non-bonding. Okay, so AB3, we already looked at that. BF3, trigonal planar, right? No big worries there. What if we have something like AB2E? where around our molecule in something like SO2, we have two atoms that are bonded to the central atom. Those are our oxygens. The A is our sulfur. And then we have a lone pair, AB2E. So that's going to look like this. Now, the electron pair geometry is going to be influenced by both the bonds, the bonding electrons, and the lone pair. So that's still going to be trigonal planar. However, if we look at just the bonded atoms, we have bent. Okay, do you see the distinction? Yes, Rachel, that is exactly it. And Rachel just said it, but let's look at that all over again. So this is the NH3 molecule, right? If we consider all the bonding electrons, we have two bonding electrons here, two bonding electrons here, two bonding electrons here, but then we have a lone pair here, right? All of these things are going to exert their force on the distribution of these individual atoms in space. And it's going to end up giving us a tetrahedral structure if we consider all of them. But if we just want to think about the actual bonds, we have trigonal pyramidal. And that is the difference for NH3 between the electron pair geometry and the molecular geometry. What about something like this? This I can tell you right now, it's going to be water. Because what do we know about water? Water has two bonds and two lone pairs. So we're going to have our two oxygens as our bonding. Our two hydrogens as our bonding. Oops. This is going to be our hydrogens. This is going to be our oxygen. And then we're going to have two lone pairs. How does that look in terms of electron pair geometry? Well, it looks tetrahedral because in terms to orient this in space. But remember, just as a little refresher from a slide, what's the bond angle of tetrahedral, did we say? Bent, Christian, is like you took a stick and you bent it. That's all. 109.5. How about in this molecule here? What would you predict if we have these two lone pairs? We just went over this, but I just want to make sure you guys are paying attention. What would you predict about this bond angle? It would be less. It gets smaller because of that lone pair, the strength of that lone pair repulsion on these bonded atoms. Okay, so bent, Christian, we're just looking at, doesn't that look bent to you? Imagine something linear and then imagine something bent. Well, that's exactly what we have here. So if we think about how the hydrogen is oriented to the oxygen is oriented to the hydrogen, well, it's bent. The molecule, those bonds are bent. That's all that means. Don't overthink it, really. Just go with the flow. Okay, so now AB5. This is, notice we did AB5 before, right? But now we're going to consider as we go down the list here, what happens if we have fewer bonds and more electron pairs? That's kind of the scheme of what we're going through here. So what's some example of where we have 4 bonds and 1 lone pair of electrons? Well, that could be something like SF4. And if we consider that in total, this has 5 things around it, 4 bonds and 1 electron pair, well, it's going to be trigonal pyramidal. Remember, there's never going to be any difference. As we go on down the line here, I'm just going to bring everything up. All of these are going to have the same electron pair geometry, because in each case we have 5 things around our molecule. Where things start to change is when we start considering just the molecular geometry. Lone pairs, you can think of them really as kind of like free agents. And by definition, bonds tend to be a bit more stable, and they're already experiencing some positive attraction to the nucleus. So, yeah, lone pairs by definition are going to exert more repulsion than bonding pairs. Okay. This starts to get kind of complicated in terms of the geometries. And I'm not going to be as, gung-ho for you to know things like distorted tetrahedron and T-shaped as I am the stuff that we've covered up until now. Well, Samuel, to some extent, it really depends. The example that you really need to know is where there are electron, it is true, where there are electron pairs, that will tend to distort the geometry, but it really depends a little bit on the particular shape that we're talking about, okay? So that's a little hard to answer. The ones that you're really going to be expected to know are the compression of those bond angles in things like ammonia and water. We're not going to really dig any deeper than that. Although you can see, in order to answer your question though, Samuel, I mean, look at this, what we call T-shaped. Notice how these are actually pointing in a little, which is undoubtedly, it's not a perfect T, right? This is undoubtedly an effect of the fact that these lone pairs are pushing this in a little. We're still calling it T-shaped, but it's not a perfect T. I just want to go back one. Yeah. So we have, so for this case, we have the AB4E, we have, if we have, what is an example of this molecule? It's SF4. It has, in fact, if we looked at the Lewis structure, it would have 4 bonds and 1 lone pair. Molecular geometry is going to be what? Trigonal bipyramidal. But if we just consider the bonds, we have the distorted tetrahedron. Duck foot. Don't put that on the exam. And then we just looked at T-shaped, right? That's a case where you have 5 things around your molecule, 2 lone pairs. In this case, when you have 2 lone pairs and 3 bonds, you're going to get T-shaped. Okay, this one's kind of interesting. This is a little bit of an unusual molecule too, I3 minus. So once again, 5 things in total around our central molecule. So nothing has changed in terms of the electron pair geometry, still trigonal bipyramidal. However, our lone pairs are going to be distributed around the perimeter of this molecule. And interestingly, we're going to end up with a linear molecule here. last gasp. Whenever we have 6 things around a molecule, geometry is going to be octahedral. But we're going to reduce one by one, just as we did on the last slide, the number of things bonded, and we're going to successively increase the number of lone pairs. So in this case, we go from, with something like BRF5, we go from octahedral to square pyramidal. If you think about it, this would be kind of a square pyramid, right? Okay, that's one example. Another example is we're taking away a bond, we're adding another lone pair. We're going from octahedral to, what's this going to be? This is obvious. This is kind of obvious. What's this going to turn into? If you had to come up with a name for it. Planar square, beautiful. We actually say square planar, but that works for me. Square planar. Here's the whole ball of wax. Now, the ones I'm most interested in you knowing, I am circling right now. Oh no, my pen battery's low. So for the molecular geometries, you should definitely know these. You need to know trigonal planar, you need to know tetrahedral, you need to know trigonal bipyramidal, octahedral. These are the ones that I'm going to be really less inclined to annoy you. I mean, I don't make promises, but this stuff, you can worry about it somewhat less. Okay, so we've covered all that. Now the question is, though, how are you going to use this in a problem-based setting? If I ask you to develop the electron pair geometry and the molecular geometry for a molecule like ammonia and ask you to comment on the bond angles, what's going to be, how are you supposed to tackle that? So now that's exactly what we're going to do. We're going to work on how we can predict molecular geometry given some compound. And the first thing that you're going to want to do for whatever compound it is, the Lewis structure is still very useful. Why? Because the Lewis structure will tell us how many bonds and therefore, and also how many electron pairs. And we need that, as we just saw, to be able to evaluate the molecular geometry of any given compound. So once we have our Lewis structure, we're going to count up the number of lone pairs on the central atom, as well as the number of bonds to the central atom. Atoms that are bonded to the central atom, because that is information we must have. And then we're going to use everything that we just went through about VSEPR to predict the geometry of the molecule. So we could do this. I'm not going to do every one of these, but let's try to work out together what it would be for ASH3. So how many, who can tell me how many total, what's our skeletal structure? I'll do that. How many valence electrons are we dealing with here? Who can tell me that? Thank you, Christian. So we have a total of 8. So I've used up 6 electrons. I must have to put. So now I want you to predict both the electron pair geometry, which means both bonds and lone pairs, versus the molecular geometry. So what is the electron pair geometry for this molecule? Tetrahedral. We have 1, 2, 3, 4 things around this molecule. It has to be tetrahedral. What about molecular geometry? You can go back and look. Not bent. We have 3 bonds, Atsuko. Water is bent, but we have 3 things to consider here for the molecular geometry, right? 3 bonds. Let's go back and take a look. It's like NH3. See how we have these 3 bonds forming a trigonal pyramid? So your instincts were right, Atsuko, but you weren't quite there. So this is trigonal pyramidal. Okay. So that's the kind of distinction you need to be able to make is between this electron pair geometry and you can even practice like drawing this stuff. It can be helpful. This is something you'll do if you go to organic chemistry. You can sort of practice. It's a little hard to do. I'm doing it sort of from a distance here from my computer.
Excuse me, Professor?
Yeah.
Will we be expected to know these shapes and identify them?
Yes.
Okay.
I just circled a bunch of ones that I said were more important to me. But when you draw this like this, you're kind of showing this hydrogen coming out of the plane, right? I mean, that's the idea here with this wedge. And this one is supposed to be retreating from the plane a little bit. So just to give you an idea of, this is not just a flat molecule. Okay, so let's look at some of these other examples. This we just did. What about OF2? So what's the, we already, you would have to do this Lewis structure yourself, but what is the electron pair geometry of this going to be? Says it right here. No. 4 things around this. Oh, wait, that's from before. Your trigonal pyramid were from before. Sorry. 4, I just got lost in chat. 4 things around this molecule, tetrahedral. But what about electron pair geometry? What would the electron pair geometry of this be? What does that look like to you? Bent, not linear. Diana, remember, these lone pairs, it can't be linear because these lone pairs are compressing this bond angle, right? They have an impact on the structure. That's why this is tetrahedral. And this is bent because lone pairs force these bonds together. What about something like ACl4 minus? Well, this one's a little bit weird. We don't have to take into account this negative charge. You might think that somehow you do, but you don't. So this simply has 4 bonds, right? Therefore, It's going to be, and you can read all this stuff. I mean, I'm not going to read this to you, but this could help you. So ACl4 tetrahedral geometry, 1, 2, 3, 4 bonds. That's really all we need to know. And notice there's no distinction here between electron pair geometry and molecular geometry because there's no lone pairs to take into account. We looked at this molecule before. This is kind of a strange Lewis structure. Yeah, just bottom line, you just don't need to. You can ignore it. There is one thing I want to make a point of, though, that I haven't really talked about. If you have something like, and this is an important point, so perk up and pay attention here. This is our Lewis structure for CO2. I've kept saying if you have 4 bonds that you're going to have a tetrahedral molecule, right? I've said that over and over again. Or I've said if you have 2 bonds and 2 lone pairs, or if you have 3 bonds and 1 lone pair, you're going to have a tetrahedral molecule. This most certainly has 4 bonds around the carbon, but it is linear. So what does this mean? It means we simply, at this stage of the game, until we learn more, if we see a double bond in our Lewis structure, we're going to treat it in terms of the molecular geometry like a single bond. So CO2 is linear. Is everybody happy with that? Now I strayed from the actual problem at hand here, but this is an important point. So if you have a Lewis structure and you're trying to figure out the VSEPR geometry and you have a double bond or a triple bond or whatever, you just count that as a single bond. But we're gonna take a more sophisticated look at that in the not too distant future. So what about this molecule? Well, if we were to draw a Lewis structure, notice iodine is one of those things that can have an expanded octet. But the bottom line is, what does this iodine have around it in total? It has 2 bonds and 3 lone pairs. What kind of geometry is that going to be? Should we go back and take a look and just remind ourselves how that is? I think it's trigonal bipyramidal myself. Let's go back and take a look. Even farther. Remember, when we have 5 things around our molecule, we have trigonal bipyramidal, that's our electron pair geometry, but this I3 minus molecule is linear. So let's go back. And notice that this would have trigonal bipyramidal EP geometry. But is linear in terms of its molecular geometry. So once again, we have a distinction. Very good. Now, this is another example of, we're dealing with a double bond here, but we're going to treat it like a single bond. Also notice this is C2H4, so we have different bond angles to consider. Because it's like we have, it's almost like we have two central molecules, right? If that makes any sense. So another way of thinking about that is we could evaluate the geometry around this first carbon and also around this second carbon. So let's break it apart for a minute. For our first carbon, how many bonds do we have? Keeping in mind that we're counting this as a single bond, how many bonds do we have surrounding our carbon? 3. So what's that geometry going to be? Trigonal pyramidal, right? I mean, trigonal planar. And we could, if we want to consider the second carbon, well, it's exactly the same thing. Only I'm gonna flip it, right? I think my stylus just ran out of gas. I'm gonna have to charge it up a little bit here while I'm still charging. Okay. So trigonal planar for both carbons. Everything in this molecule is in the same plane. It is a flat molecule. So this is kind of an interesting point that we're going to return to. Now, we already talked about polar bonds. So this should be a little bit of a refresher. HF is a polar bond. We know that because there's electronegativity differences between the two molecules. And it has an electron-rich region with the electronegative fluorine, an electron-poor region on the hydrogen. We also talked about this, dipole moments. So this should be a refresher. In fact, I think these slides are out of order. We already went through all of this, as a matter of fact. We've done this. Oh, no, we haven't done this, though. This is what I want to talk about. So we can actually calculate the charge separation between something like hydrogen and fluorine. There's a formula where we can calculate that dipole moment. We call this a dipole moment. And I remind you that's represented by this arrow here just below the HF. Q, if we want to calculate this, Q represents our charge and R is the distance between the two charges. This is measured in something called the Dipole, which by definition, 1 Dipole equals 3.36 times 10 to the negative 30 coulomb per meter. Coulomb meters, I should say. You're not going to have to do that. I just want you to know you can calculate an actual, you can physically calculate an actual dipole moment. So, and it's quantitative, right? So depending on charge separation and distance, we're going to get different numbers. Now, this is for the physicists among you, or for anyone who has dabbled in physics whatsoever, or even, I suppose, some kinds of math, will recognize that we could define something with that combines charge and distance as, which is a force times distance, as a vector quantity. Any vector quantity has both a has a magnitude, a size, and a direction. So will our molecule, so now we have to stop thinking about individual bonds and start thinking about our molecule as a whole entity. Because bonds can be polar, we've certainly seen that. Bonds can be non-polar, we've certainly seen that. But if we really thought about the polarity of our overall molecule, because molecules themselves do have dipole moments, some of them. Some molecules are polar, some are not. And one way that we can get at this is to understand that whether or not a molecule has a dipole moment is going to depend on the vector sum of all of its bond moments. So here is a classic example of, I'm hoping just a little bit of charge to my stylus is going to help it out here. Does this molecule have a dipole moment? Does this molecule have a dipole moment? I mean, do these individual bonds, I should say, have dipole moments? Yes or no? Yes. Does that mean automatically that if you have polar bonds, that you have a polar molecule? No. Why not?
Because you just said it was the sum of the.
I just said, my God, somebody's listening to me. I love it. Just being a little sarcastic. These vectors cancel one another out. Notice this is a highly symmetrical molecule. So with these things pointing in three different but symmetrical orientations, in totality, if we were to sum these three vectors, they would cancel one another out to make BF3 a non-polar molecule with polar bonds. And this can be very confusing to students because the minute they think that there are polar bonds, they think they have a polar molecule. And the answer to that is sometimes yes, sometimes no. But if the vector sums, if your dipoles cancel one another out, polar bonds, non-polar molecule. Now, sometimes these dipole moments don't cancel one another out. That's also quite common. And in this case, we say the molecule has a net dipole moment. We know water is bent. We just saw that. So you might be tempted to think if you drew the regular old Lewis structure, that looked like this. That these dipole moments would cancel one another out in these polar bonds because this looks linear, right? But it's not linear. Gone to some lengths today to convince you that because of these lone pairs here and here, water is actually, in terms of its molecular geometry, a bent molecule. These are forcing these bonds down, right? And we have an overall tetrahedral geometry. So in fact, if we think of how the dipole moments are going to work here, they're actually going to reinforce one another. And we're going to get, if we sum these two vectors, we're going to get an overall net dipole moment pointing in this direction. Water, you must recognize, especially if you're going to go on in chemistry and do any organic chemistry, you must recognize that water is, in fact, a very polar molecule. So this is where the molecular geometry comes in handy, and the Lewis structures don't necessarily tell the whole story. Okay. Make sense? Oh, this is the overall dipole moment for water. So we have to think of the molecular shape if we're going to understand the relationship between polar bonds, polar molecules, polar bonds, nonpolar molecules. So carbon dioxide, as I pointed out previously, really is linear, right? Because we just count these, the geometry is linear. We're counting these double bonds as single bonds for now. They're not, but we're pretending. And we notice that these are diametrically opposed to one another, and these are going to cancel one another out. Non-polar molecule. So this is another example. We saw BF3 as an example of a molecule with polar bonds and non-polar overall. Now we can say CO2 also has polar bonds, but is a non-polar molecule. So typically, polar molecules are going to have an asymmetrical shape that might include lone pairs. Probably pretty often does include lone pairs. Or is asymmetrical in some other feature. So let's just compare what, this scenario is versus this scenario. So for this first one, we have an asymmetrical shape with lone pairs. Our dipole moments are all pointing towards nitrogen because hydrogen is more weakly electronegative than nitrogen. And the overall dipole moment here is going to be going up this way. Well, CHCl3 is also an asymmetrical atom because we have Cl's versus hydrogen. Now, Cl is more electronegative than carbon. So the dipoles are going to be going this way. And hydrogen is more weakly electronegative than carbon. So the dipole here is going to be going this way. The dipole moment on this one is going to be in this direction, right? So overall dipole moment for NH3 is going to be pointing upwards as I've drawn this molecule. And here, because of these electronegative Cls, it's going to be pointing down. But you can think of both of these as the tetrahedron itself is a symmetrical shape, but it becomes asymmetric when we start including lone pairs or we start varying the atoms that are bonded to our central atom. However, what about something like do we have dipoles here in CH4? Rachel, yes. I would say yes to that. Do we have polar bonds here in methane? Does anyone care to answer that question? Yes or no? Do we have polar bonds in methane? Polar bonds, I'm just talking about the carbon-hydrogen bond. Is the carbon-hydrogen bond polar? Yes, thank you, Baruch. H is less electronegative than carbon, so we have a polar bond for each of these. Is this a polar molecule? Next question. No, because once again, these vectors are all going to cancel one another out. This is a symmetrical molecule, and the vectors are oriented away from each other at precisely the same angles, 109.5. So all those dipoles cancel each other out, non-polar molecule. So here's NH3. I just talked about that, but here it is again, drawn better than what I was showing you. Now, here's an interesting one. So NH3, we already talked about that, right? We can see that overall, the dipole moment is going to be like this because of the summation of all of these effects. Definitely NH3 polar. But what about something like NF3? The lone pair itself, note, creates its own dipole moment. It is definitely more electron rich than N itself by virtue of being a lone pair. Notice that in this tetrahedral model, however, the fluorines being more electronegative than nitrogen are all pointing downwards. So is this molecule going to have a dipole moment? Well, it turns out it does, because if we were to sum the vectors, we're going to get a dipole moment that we could calculate and devise. But notice how much smaller that is than nitrogen because of these opposing forces that we have within the molecule. Okay, so this is an easy one. Considering this molecule as a whole, does it have a dipole moment? What's your rationale for no? Why would you say no? For the people who said no, why do you say no? Someone please give me an explanation for their choice. I know you can speak. I've heard you do it before. Somebody, anybody, bail your professor out. Michaela, I'm going to make you say, because you changed your mind.
Electronegativity difference.
Yeah, this is pretty simple, right? This is not a complex molecule. I mean, we probably should think about what the Lewis structure is. It's like this. But there is electronegativity difference. I forget which one's more electronegative. I'd have to look at the periodic table, but we know there's charge separation between these two things. BF3 we already looked at. And we said all the bond angles are equal. This one is perfectly symmetrical. Even though we have dipole moments, they all cancel one another out. So polar bonds, non-polar molecule. The overall molecule has a dipole moment. Now this one gets trickier. Let's draw a Lewis structure. For this. polar bonds So what do you think? Polar or non-polar? Polar. Once again, you might be tempted to think that if you drew this as a Lewis structure, you might be tempted to think that these cancel each other out because of the way this looks. But that's not true. You have to think of the molecular geometry before you can actually get at the resultant dipole moment. So I hope that's illustrative for you. This is most definitely a polar molecule. Look at the heat map and look at these vectors. We have a resultant dipole moment, polar molecule. This would be the wrong way to consider it because then we'd start thinking that the vectors are canceling each other out, but they're not. Okay. Keller et al. Does anyone speak French here? 1224. Oh my God, I got carried away with my own